Okay, please let me know if you can't hear me, but my name is James Richings. I'm going to be leading the sessions today. We're going to cover sort of two main topics this afternoon. First off is going to be templating, and this is around how you can use templating to write generic programming models in C++. And we'll then move on to look at algorithms and lambda functions in the second part. Before we start with that, I thought it'd be valuable just to review the example from yesterday with you all. Briefly, I'm not going to do a code along this time. I'm going to share the solutions, which you can all find on a separate branch of the GitHub repository, to be able to work through and understand in your own time. But to start with, I'm just going to share. So I'm doing this off a single screen, so maybe a bit of me figuring out how to share the right things. Okay. Yeah, this will see a terminal window. Okay, and this is the code for the first step of the Morton ordering example. Just to confirm, you can only see that it's a bit small. Okay, I'll increase it in size momentarily. If you have any questions, please post them in chat. I will have to flick between screens. So this example asks you to look at implementing some classes or sort of on your own, understanding sort of the creation patterns yourselves. And what we're really looking at here is implementing a 2D square matrix which has a custom iterator, which allows you to access members in a particular ordering that will allow for more efficient access patterns. So you customize the way in which you're going to interact with this. The kind of tricky bit in terms of all the bit twiddling and how you access things has been given to you in this file. We're going to kind of skim over a little bit of some of the complexity here because it's not what the focus is. And what we're really interested in is the type of iterator and how we go about implementing that. And the functions we're going to mainly kind of focus on are this sort of encode, decode throughout this example. If you're interested, this is also included and you can read through. It's commented quite well, so you can figure out what's going on in the specific set there. But okay. So we want to do a simple implementation that requires some power of 2 number of elements. We don't want the matrix to be resizable. We don't want the matrix to be implicitly copyable, but we must be able to duplicate the matrix with an explicit call to a member function. So that means we're not going to overload an operator to do that. We're going to explicitly call a new function which does that, so that it's explicit to us in our code whenever we've made a duplication of this, and we're not copying this implicitly. In order to do this, we need to first of all decide on how we're going to store our data. So that one of the first do's are we're going to use a a unique pointer and store an array of elements T. Now, before we go into this in any more detail, this example does use templating in its construction in order to generate a number of the tests. We'll come on to templating momentarily, but what this is really saying is T is just kind of is a variable, it's a wildcard of a type. It can take a value of your choosing, but you should just think of it at the moment as a double. And we'll come on to explain the detail of this in the next set of lectures. The point of here is we're just taking a simple array and we have it as a unique pointer so that we avoid copying it by default. And what this choice doesn't have, we don't have to choose this, we could choose a standard vector, but that implements copying by design. And in this class, the next sort of set of decisions to make is A, is how we're going to implement the constructors. So we have default initializations. Okay, so we're just going to say our rank, which is the size of our matrix, will be set to 0 by default. And this notation here with a colon underscore, this is the initializer list. This, when you call a function, happens before any of the code is run. So you could imagine writing something like instead, where you'd say rank is equal to 0, but by sort of convention, we use the initializer list instead, and then initialize the value of rank, which is a data member of this class. If we just generate a default matrix as 0 size. If we give the matrix any size, then we can call a different constructor where rank takes the value, we input it, but we also now make a data member that's the array that stores the information we're capturing in this matrix. As a new pointer of some type T, an array of, as we discussed, doubles. And the size of the matrix is going to be a square matrix, so it's going to be R times R. So the rank of the matrix times the rank of the matrix size. And in this constructor, we're going to assert that our rank is set to be a power of 2, as we've required by this. The next question is around how do we encode our requirements around not copyable. So if we're going to start looking at the sort of copy constructor, copy assignment, move constructor, move assignment, we need to provide all 5 to go by our rules that were discussed, I think, yesterday or Monday afternoon. And we need to explicitly delete the constructors that we don't want to allow. So we don't want to allow copying, so we explicitly write, we're going to delete these. So no defaults are created, and that we don't generate behavior that we don't want to design into this matrix class. So that covers copy and move. However, we're just going to set the defaults. The reason we can do this is because the data members of this class have sensible default behavior. So if we look at how a unique pointer behaves, we could go to CPPRef and look up that functionality. And by doing so, see that it operates with, by default, it implements sensible versions of move. And therefore, when we tell the compiler to implement this class, it will use the default set by unique pointer, and that's acceptable for our purposes. Same with the destructor here, the default set by unique pointer allow us the functionality that we desire. Okay, so then we need to provide some more information. If I'm correct, we wanted to look at element access next. So I will come back to duplicate in a moment. We obviously, if we request the rank, we just return the value of the rank of the matrix. If we want to turn the total size, it's just the size of the number of elements of the ranks times each other. That's pretty straightforward. When we're looking at element access, what we're using is the encode functions provided in the bits I think you require that. I think you do require the no exception. I think there's a requirement from the standard. I'll have to have a think about that one and get back to you later, maybe after the break. I think I need to look something up quick. Okay, rank is just this way of determining size of the matrix in question here. So if you have a sort of the number of elements in each axis, you can determine as the rank of the matrix. I'm having an n by n matrix, so a chessboard 64 is 8 by 8. If that helps. The way to think about this. No, the rank is 8. (64) would be the number of elements in the matrix. Okay. So these. Yeah, an R matrix. Okay. So what encode and decode are allowing us to transform between the position in our array and our XY coordinates of the matrix. I'm not going to go into the detail of how the bits are being filled here in order to do the Morton ordering, because that's not really what we're trying to focus on. We're using this as an example to discuss how we can build classes. Effectively, we want to access a particular element. We provide the ij coordinate in a grid. And this is then we use our encoding mechanism to take those coordinates and return them to a position in our array. And in the first case, we have a constant access, which means we're not going to edit the returned reference. And we have a mutable, which does allow editing. We also have raw data access. So what this allows us to do is get the pointer, the unique, the raw element location, and return that. Get function here is a member of the unique pointers. It's a member function of a unique pointer, and that allows explicit access. As you can see here, that what this class is doing is entirely around control of how you access the data and how you represent the data. And even though we just have a simple data array, we can use this complexity to manage how we're going to allow access in our program. And this is kind of one of the powerful things that C++ allows you to control over this at quite a fine-grained level. So I said I was going to come back to duplicate. And here what we're doing is we're saying we're going to make a new type of matrix, and we're explicitly making a copy. And we're going to copy the data elements from data, which returns us, let's remember what we had, a pointer to the data, remember, so that'll be the start. To the end, based on the size, we're just going to step over that. And we're going to place this at a pointer in the answer, at the location of the answer object, which we just created. And that answer is going to be returned. So that is a new, and we've explicitly duplicated the matrix here. So what you're doing is avoiding potential performance hits from implicitly copying this object by accident, especially if you've got a matrix that's very large, you want to avoid that to maintain performance. Okay, that's sort of step one in a nutshell. Step two, looked at this slightly differently. And in this case, we have an iterator construct a matrix iterator to do this instead of, which does, so it means it does this quite slightly differently. The matrix class itself is much the same. There are some slight differences that we'll come on to. I think the key thing to mention at the top here, and we'll come on to using in the next lectures, but it's just a way of aliasing. So we're just going to use this to be able to simplify the naming convention of what we're going to call a new class, matrix iterator. And let's discuss the matrix iterator class. Okay, so this defines an iterator object that allows us to iterate through members of the matrix class, and it gives us access so that we can, instead of encoding the access patterns explicitly in the class itself, we just access the iterator, and then we could choose different ways to iterate through the same data depending on the iterator used. So it generates a separation of concerns. What you're effectively doing here is implementing the members required in order to generate an iterator. So we have functions for accessing x and y. Let's just look at the data members first. So these are a pointer to the start location of the matrix and a pointer to where we currently are in the matrix. We can then use these to know our starting point and our current location. So we can then use these to calculate our x and y coordinates based on them just being the difference between the start pointer and our current location. And we can return that. We're using this pack function, which is held in the bits header file in order to do the conversion. But you can see how your location in Z is now just related to your element number you are along your array is just directly related to the difference in these two pointers. We also want to do something like comparison, so we need to make sure that we can identify that the pointers are the same. Our iterators are at the same position. And comparison. So each of these elements allow us are quite kind of obvious. We're just dereferencing the current pointer. We're pre-incrementing everything there ends up being effects on the pointer location, which is held in underscore pointer, and that holds the information about where you exist in your current matrix. So you don't interact with how you need to do this, and instead the matrix class now is free from the implementation of the movement itself, and instead, when you're doing things like copy, you're just grabbing begin and end functions that you would do when we're in iterations of sort of standard containers as before. So the exercise is to really go through this in detail and implement each piece of functionality. The solutions are available, but effectively what you're implementing really is a custom iterator for the matrix class itself. And separating this out allows you to group the functionality in separate classes. Okay. So I'm just going to stop sharing that and then move on to the section on templates. I'm going to do this horrible thing because I can't see stuff from people send comments. 1 second, let me just stop sharing before that just drives everyone mad. Thank Kevin. Okay, so Kevin's posted the slides. Okay. So what's the motivation? I think the best, so the example here, I think we actually had this brought up by a question by, I think it was Elena or someone else on Monday, if I remember correctly. You had multiple combinations of writing this simple sum function. And what you end up having to do was implement this multiple times. And you had to explicitly specify the types of the inputs to the function. By the time you had multiple combinations, this became quite laborious. What you really want to do is minimize duplication of the same code as much as possible, because you generate potential divergences, and that can propagate errors if they're not all taken care of when corrections are made. What templates are doing is they're not programming them, what we describe as meta-programming. You're asking the compiler to generate the code for you based on a set of rules. And so how would the simple sum example look? This then turns into we can turn this into a template function, which has the structure at the top here. So we need to declare to the compiler that this is a template. We then say what sort of wildcards, what can change about this, what can the compiler pattern match to effectively, with the type name T. So T is now the wildcard. Its return type, the return type of sum, the function sum, is going to be of type T. It's going to take 2 arguments. Both those arguments are going to be of type T. And then it's just going to run simple addition and return that. So we have some examples below. The type name here can also be used instead as class. It's the other word that could be used here, and both work equivalently. The compiler, when it sees a use of this code, so in the example we have the 2 lines are just going to print to standard out. Some then has angle brackets unsigned, and with the other line we have some float in the angle brackets. And what you're specifying there is the explicit type that you want this call of the function to take. And the compiler will then, when the code is being compiled, generate a version of that function with the specific type needed, and then link to it. But you can also do is it can, in some cases, implicitly determine what the type T should be. And here I think it's using the argument list in order to determine that, and therefore the return type. And the return type of the expression A plus B. So you don't always need to explicitly give it, but I would say it's good practice to, because what this tells you as the reader of the code is that templating is being used here. For simple things, it's maybe not so important, but it does help to sort of flag to someone else that what's actually being used in this particular case. Now I have a quick example of that. If I just find the right screen. Okay. Great example. Okay. Okay. So here you should be able to see it's a bit bigger. People, that's implementation of exactly what was on the screen. So I just want to show this in practice. You can see here we've simply just added example 1. Very simple. We've added an unsigned 1 and a 4, and we've printed out an unsigned 5. But exactly the same function has chosen an entirely different type object and done a similar function, performed the same functionality but on a different type, and we've had to write the code to do this once. And this is where this the powerfulness comes from. Now, this does rely on the fact that the addition operation inside the sum knows how to be applied to the different types that we pass into it. And we'll come on to that in an example at the end of this lecture section. Okay, let's go back to my slides. We can also do this with classes as well, as we saw in the matrix example. We treat this exactly the same way. What this does is for the entire class now gives us a template parameter T, so we can make multiple versions of the same class object. The classic example here, we have in this case a myArray. It's just some array that we've created. But you could do, but from the standard template library, the standard vector then has angle brackets, and you provide a type to that, which allows you to make vectors of all numbers of different types of objects, which is quite a common pattern you'll come across when coding C++. And that's using templating underneath to provide that flexibility. So it's really this sort of angle bracket syntax you'll see whenever you're sort of engaging with templated objects. The other important thing, as I mentioned when we were looking at the matrix example, is around the using word in declarations. What you're doing is providing a type alias. This allows you to turn very long and complex type information into simple identifiers to make your code more readable. This has lots of advantages, and sort of a good example here is if you're, I mean, this is taking a templating case, but to say you had a vector, sort of multiple layers of vectors, or the matrix had a matrix was a matrix of vectors, so it was a matrix type of a vector type of ints. Writing that out each time is quite long and laborious, and you don't need to do that. So you can use the using the keyword to sort of replace that with something more meaningful for you. This could be the representation of a physical quantity. So it could, that combination could represent a particular structure in your simulation that you're interested in, for example. Here we're using it to redefine the template parameter t into something that has semantic meaning in terms of what each of these sort of, we're taking versions or sort of adjacent types to the template parameter here, but we're taking a reference version of it, we're taking a constant reference version of it, and we're encoding that in something that's readable to the human as they go through the code, which may make a lot more sense and to you as you just sort of look at this quickly, opposed to having to remember what every combination of the characters represents themselves. I think one really important thing to mention with these templating types is that will come on tomorrow in the, especially in the discussion around the eigen package, is that what they provide only applies in the scope where it sits. So if there was the class definition in one file and we import the header, we don't get namespace mangling. Yeah, so I'll come on to this in a second. You usually, yeah, you need to make sure that you define the templates once and only once. You don't want to have multiple strictly you're allowed to with templates because the compiler is going to generate the code, and therefore can generate multiple instances of something with the same name in each translation unit. And if you end up with different versions of the templated class in different translation units, it will just, the compiler will just pick one. So while there's no strict sort of requirement that everything is only one definition, you have to ensure that yourself, if that answers your question. But yes, you'd normally keep the templates in a header file, and then the specific implementation of them in a sort of a related header file as well, so that you always have, they always need to be included whenever they're being used to replace an explicit case of a given template. As I was saying about where this will sort of, why are we talking about templates in great detail here, and why, well, they have some uses. There's some explicit cases, especially with the eigen package we'll discuss tomorrow, where this relies heavily on templating in its implementation, and can gain a lot of optimizations from that, especially around using explicit. Something we'll just come on to, I think it's the next couple of slides. I'll come to that in a second then, sorry. So yeah, as we're discussing, where do you put your implementation? This is not executable code. This tells the compiler how to create the code. So the definitions must be available in the translation unit of the user of your template. So you want to put this in the header file. You can either define in place or at the end of the header file, or an equivalent header file so that you separate, as we call it, implementation.h. It's kind of common that you then include in the header file with the sort of definition. That's kind of the standard structure to do, but you don't want sort of copies. Yeah, so the one definition rule, everything normally has to be defined exactly once, but we can have multiple definitions of templates, and the same with functions marked inline. You could have multiple repetitions of the same template in different translation units, but this could cause you problems at linking time, and the compiler and linker will choose for you, and this could give you unexpected behavior, which you want to avoid. But the difference here is that it's not going to complain at you at linking time, so you need to be careful to do this yourselves. Okay. So we talked about a little bit about type deduction earlier, but when you're returning from functions, you can't specify what t is going to return when you don't know that ahead of time, because if you didn't give, okay, here, if you just have the two lines in the middle of the page here, if you knew that x and y were both integers, when you were calling sum, then you'd probably have surmised that z is also going to be an int. But say this depended on a particular, so the classic example here is, do I want the precision of my simulation to be float or double? Float will be faster, but maybe I have worse rounding errors or some other some potential issues. You might want to set that as a parameter more widely, and therefore the particular return type z you don't know ahead of time. You may want to provide, instead of providing an explicit definition, you want to let the compiler decide for you using the auto keyword. So it examines the return expression and tries to choose the correct return type for you. So we also, as I sort of hinted when we looked at the using keyword, we have sort of type deduction. And this means that when you have the template parameter t, you don't just have to use t as it is, but you can also sort of decorate it with your usual type, sort of related types. So we looked at reference and const reference when we looked at the using keyword, but you also had forwarding reference. You can also use this in combination with other classes. So we talked about standard vector being a common usage of templated types. You can pass templated parameters into other templated classes, and this will work quite nicely. You'll often see things pass standard vectors which depend on the class type. You can imagine any number of operations you want to apply to a set of vectors independent of their specific type that wouldn't affect that operation, and therefore you can provide the parameter as a templating parameter to each of the arguments, which are vectors. And you can see how this can quickly nest to make sure that so that any particular parameter you want to change can, or the type of the parameter you want to change can be provided and allow flexibility that way. I think one thing that isn't explicitly shown here, but it's very important to highlight, you don't just have to have one templating parameter per class or per templating function. You can have multiple, which allows more flexibility. So before I come on to that, you obviously don't want to keep having a multiple, because the sort of space of combinations is quite large, and is that really the best use case for, are you going to have variability in all those large number of typed arguments, or do you really just need a couple and specific implementations of the rest? The other thing sort of mentioned, you don't have to have type parameters as template parameters. This is quite important, and this will be shown in detail in the eigen examples tomorrow. You can have integers, pointers in enums in sort of more currently used versions of C++, and literal types and floating points in C++20. What this allows you to do is, as the example shown here, provide explicit sort of lengths and sizes of matrices, vectors, and therefore specific sort of operations can be done with a given, ensuring that they only ever operate these operations on certain sized objects. And this can have consequences for optimizations which you might want to perform based on certain parameters, and can be very useful when designing templated classes or functions. So there's quite a lot of detailed rules. Meyer's Effective Modern C++ is quite a good reference for this, but some rules of thumb. Whenever you want to copy the argument or not, if you don't want to copy, add a reference. So basically treat your templated parameters as you usually would. You can affect things with constants. If you want exactly the type of the expression, so add the double ampersand. This is a forwarding reference. Capture that information for you. But you can apply these templated parameters well as you would do in other cases. Okay, and we've already discussed the auto keyword. Okay, I have a brief example now that I want to go through for sort of 10 minutes, and then we will take a break because the second section of today is a bit longer. Before I do, is there any questions on that content? Oh, sorry, I realized I misunderstood your question earlier, Stefan. Yes, the using operator only applies to that scope. Sorry, I thought you meant something else. Yeah, you don't want to. Yeah, you don't want to get main namespace manually. Exactly. Okay. A forwarding ref takes type information with it, is my understanding. It's not something I've used particularly commonly myself, but the best place for more information now would be the C++ reference. We'll have a detailed breakdown for you. If one files two different types into a template function, how to specify that? So instead of a single, let me just find this code example and I will write this little piece in there. Okay, this is the piece that I want. You need two type names, so it would have to be template type name T, comma type name U. So let me just share. So delete some of this. So what I wanted to do is kind of code along with you with this, but unfortunately it's not set up currently to do that in a very reasonable way. So what I'm going to do is show you in a simple example of a data class here. So just to directly answer the question, I can write template class or type name T and class or type name H and use both. That's how you apply multiple types. In this example, so this is not part of the course materials at the moment, but I will add this. We're going to take a simple example template here of a structured data. So we have a templated data structure which has two member functions, two member data types. Two data members, that's what I'm trying to say. Underscore X and underscore Y. Okay, I've got some default constructor, and I've got a specific constructor which is just going to initialize X and Y with the values passed in. Okay, I've got a simple printer, which is simply going to, if I call it, it's simply going to print values of X and Y out and print what they are. And sort of interesting bit here is I've got an operator overload. So what I'm saying is I've got an overload of the addition operator, which is going to take a constant member, constant argument of this object data with some type T. Maybe it's still font size. Of course I can. Sorry about that. Yeah, I did it for the other monitors, but I hadn't changed this one. Okay. And this is going to print the statement saying we're inside the addition operator for this particular class. I'm going to make a new data object temp. I'm going to add the input argument values of X with the X of the current type. So this will just add two of these objects together and return a new object of this data type. Okay. I have a number of examples here, but I'm just going to comment these out quickly and rewrite this main function so we can do these sort of one by one. The other thing I need to talk about is test. Here, I want to simplify what I have. Okay. So focus on this particular test. So here we just have, this is going to act as our sort of like simplest implementation of this, of a specific run of this addition. And all it's going to do, it's going to, and this is a templated function, which has to take symbol type T, template argument. It returns a void, it doesn't return anything. And it's going to take 4 arguments. They're all going to have the same type T. We're then going to create 2 objects of class data. And we use the parameter T here to denote that they are going to have, so these T's could be ints, or they could be strings, or they could be floats. We're going to create 2 of them, N and M. and a third Z, which is going to be output. And I'm just going to write a simple run of the addition. This add is going to use the addition operator implemented for the class, and we are going to print out the result, the values of Z. No, it's a naming convention. So the type name T and the class T, it's convention. It doesn't matter. They're both synonymous, and depending on which code base you look at, different people choose different things. Try to stay consistent with whatever code you're looking at the time. It's one of those sort of annoying things about the language that sort of exists. So if I just take a simple example of doing why are you failing now? Wonderful. Anything I don't need for this particular case. So if we look at what we at doing here, so we're simply adding one. So this particular case, we're going to add. We're simply going to run tests with 1, 2, 3, and 4. So we find out the tests we're specifically using. This is going to mean we're going to make a data object with 1 and 2 and 3 and 4, which we're then going to add together. And we look at the implementation, all that's going to do is take 1 and add it to 3, and 2 and add it to 4. And then we get 4 and 6. Okay, that's one specific implementation of the template. But we can, again, then you look at multiple versions of this. So like we did before with the example of simply the sum, we can then take things like tests and we can look at the float. And recompile. The window. And the operator, we run the same operation, but the code has made a different version using the template for the float case opposed to the integer case. We can take this one step further. And we can do a standard string. And we can just do a very simple and recompile. Okay. And here we've used something that really shouldn't, that we wouldn't really expect the addition operator to maybe make sense for, but we'll explain why what it's doing here. But an entirely different type, not something that's numeric, that you wouldn't sort of a thing. Oh, okay, it's just sort of, it knows a float is something like an int, and it's reinterpreted. This is something entirely a different type, but it still performs the same operation of combining the values. Here it's just doing string concatenation. The addition operator simply does that in this case. But the template can be used for a wide variety of input types T that we provided, and overload them in order to give an example, give a particular implementation in a piece of code you're writing, allowing you to generate a lot of flexibility from a single section of code or class or function in your particular code base. So there's quite a lot of power there in what it can do and allows you to do. The sort of final example here is to look at something that maybe looks very similar, but does something a bit odd. And this is to do this, but instead of this, to car, which we'd kind of expect to make sense. I'm doing something very similar to the string case. I get kind of nonsense out of this. And this is because, well, in the string case, you have a sensible overload for the addition operator. With a character, you don't. And therefore, it's doing some interpretation of that character string and finding an overload of the addition operator, which there maybe doesn't apply a sensible result. So you do have to be aware of the fact that this is automatically generated code, and while what you may be implementing looks sensible, when you use it in specific cases, does the implementation you've written really protect you from unexpected consequences? So there's a little bit of wariness that needs to be taken with this, but it can be quite a powerful tool in order to automate some of the code generation in cases that you may be interested in. Especially when you have large objects like matrices or vectors, when you don't really want to be writing out specific implementations of quite long and complex classes, because if anything goes wrong in a specific implementation, you'd need to update every single version of it. Okay. I have a question in the chat. Okay, so on the topic of multiple parameters templates, yeah, it is just, I have to remember this because I think it is, I think the things I was doing in that example, I had that case and it was breaking on me, so I ended up with multiple versions of different names for those. Though I'm trying to recall, yeah, I don't think you can just have it for the with the constructor interface does crash. I'll have a think about it during the break and come back to you. I'm going to take the break slightly earlier here now because the second half of today's lectures are a bit longer. So what we'll do is we'll come back at 35 minutes past 2 and start again then. If anyone has any questions in the chat, there's no specific example for the template case which has gone through. But the sort of matrix example for Morton ordering does implement some of this. So it maybe has some templating in it. So having gone through these lectures, it might be worth going back to that and just having a read through if you have 5 minutes and trying to see how templates have been used in that example. The solutions are in the solutions branch on the GitHub repository. So you can see the full solutions we went through at the beginning of this session. But for now, we'll just pause it there and I will there's a couple of questions from the chat that I'm just going to go through, and I'll try to get back to you during the break. Okay, see you all in half an hour. Okay, I think we're all back. So I'll start on the next section. I'm going to slightly change the ordering of these slides because I think this way around will work slightly better than it did last week. So there's 3 topics we'll talk about this afternoon. The first of them is going to be traits. So this is type traits. We will then go on to talk about algorithms and lambda functions. We'll then take sort of half an hour to try an exercise independently, although we'll be here to answer any questions in the chat. Finally, I'll walk through that exercise before we finish, if we have time, and just review anything. If I don't get a chance to do that this afternoon, I will endeavour to come back tomorrow at the beginning of the session and go through that in detail. So I've kind of moved this around slightly because this follows on quite nicely from our discussion of templating types and what type traits are. It allows us sort of the if then else of types. So we've talked about a way to do something very generic with types, but we'd like to control logic based on types as well, and configure that. You can sort of specialize depending on type what you're going to do, and this can allow you a lot more control. There's a standard header for this called type traits, and this has a lot of detail. I'm going to kind of talk through one specific example really related to HPC and kind of how you might, a definite example of where this can be very useful to kind of do this sort of control. So an example here would be something like, is this a pointer? And this example, if there's a standard, is this a pointer on an int? Its value would be false. We have sort of numeric lists of lots of parameters from built-in types, such as the largest and smallest values, whether they're integer floating types, etc. There's lots of traits that you can look up in the standard library, CPP-ref, but that sort of gives a little bit of a flavor of what this can return you if you need to inspect the types themselves. The specific example I'm going to give, first of all, I'm going to introduce something called a package called MPI, or sort of a standard called MPI is probably the best way to put it. It's called Message Passing Interface, and this is quite common when we do large simulations, specifically on HPC systems, and many of you may have come into contact with this already. What you're interested in doing is passing messages between multiple compute nodes in order to spread your calculation over more hardware, either to access more total memory or so you can perform a larger simulation, or because you want to gain some performance at scale. What this effectively does, I'm not going to get into the details of this library, this is complicated. We have a separate course on that we run either in an open version, or we run talk courses like this quite frequently. But it does have one sort of notable feature. It's a good demonstrator of why sort of controlling types can be quite useful. Effectively does it sends a message across between two computing nodes. So here we have an example class, which is going to be a wrapper around this. So it's going to control this resource in a class called com. It's going to have a send function, which is going to send a vector of some type t. You don't know t a priori. We're going to set up some communicator to tell how we're going to communicate between different things. That's kind of an implementation detail. And we're going to send a very simple vector of just 2, 4, 6, 8. And we're just going to call send. Now, all we've had to provide there is the data, the destination, and some reference tag that says which message this is. And you can think of as a simplified implementation of this particular send to be as follows. It's just going to call the MPI the library send. It's going to reinterpret, cast the data to some void pointer. But we need to provide the MPI library with a specific data type, which we've got here as block capitals data type. And depending on what you're sending, that's going to change. So how do we fill this correct typing? Because this isn't a sort of our standard type, this is a type specific to MPI, and we need to make sure this is the correct one in each case. So for an integer, that's going to be an MPI int. And you can maybe see where this might become quite complicated. If we've got lots of types, say m different types, and many MPI calls, n of them, to be wrapped, we need to have an m by n number of specializations of this particular class, these particular functions in this class, and that's quite overbearing. And how would you influence custom types? You'd have to mess around with this quite a lot, and that's not sort of ideal. We want to reduce this complexity that we've generated here. It's good to have this interface to kind of separate off MPI from the rest of what we're doing, but this is generating a lot of work for us at the moment. So instead, we can create a traits class, which is going to tell our function how to handle different types. So here we just have a simple data types, data type traits structure, and it's going to return an MPI data type with the function get. And all this is taking in is some type t as the template parameter, and we're not providing a default implementation of the get functionality of the structured data type traits. So you can see now how this com send now looks. It takes some class template t, and instead of taking a specific MPI data type, it takes data type traits of t, and it calls the get function. And then, in order to do the implementation, we just specify a number of specific versions of this get function for a set of implemented sort of standard, in this case, types, so int, float, and they return their corresponding MPI types, MPI int, MPI float, to be able to communicate the data. What's really nice about this is that if we haven't implemented a specific type, that when we try to communicate, we'll get a compile time error. And this gives an example of how we can use some trait manipulation, so type manipulation, in order to take advantage of both the templating and reduce some complexity, even though templates may naturally think you increase the number of the complexity and you condense it down into a specific template example. You can reduce this sort of the number of versions you're generating in this particular case. Okay, that is to try and sort of summarize a little bit more on types themselves. Otherwise, it's kind of a little bit like a bolt-on at the end. I'm just going to go back to the beginning of the slide deck. So, what we're now going to discuss for the rest of this lecture and then the example is a little bit around iterating through vectors and how we can use some of the standard algorithms provided to do some things in a slightly different way. So if we just do a bit of a recap of some of our ways we would write simple for loops, we have sort of three key common examples that we're used to. We have a C-style iteration where we define the starting point, some specific sort of termination of the for loop, and some iteration through the loop. We have older C++ style iterators, where we define the beginning, termination, and increment of the iterator, and sort of more newer sort of range-based for loops that have become quite popular. This is kind of more reminiscent of Python for those who have used Python more commonly. But the standard algorithms library provides us with some more options. This provides us with like sort of 100 function templates that implement certain algorithms, such as things like count elements that provide elements based on a condition. These use iterators to specify data they will work on. So the example given here is include the algorithms library, take a vector of integers. We're going to read in from some unspecified operation, and then count from beginning to end of that data zeros, and return that into the output integer and zero. You could also have a different function, which is called prime, defined, which determines, it takes a single integer argument, which is going to be the value at each step through the iterator on data, from its end of data, and then apply the function to it, and that's going to return a true or false value, and it's going to count based on that prime function which has been defined. Yeah. About using auto as like, why would you ever not use auto? Was it bad practice to use auto if we know the type? You can quite commonly use auto. This, I think, this is kind of it's a little up to you. I think there are specific examples, and I could probably write several that I'm not going to jump into that right now, but maybe we can have a discussion later around specific cases. How is your code if you use auto everywhere? Cases where you have to use auto, cases where you specifically know the return. If you do something unexpected in the function call, is it going to get barred? And what actually should have happened is that the return did match the sort of the view of the argument was receiving it, and then it should fail and maybe it compiled. So auto gives you some benefits where you don't really have to know, but you're sitting on some ability to catch some bugs potentially if you just use it too often. It's a trade-off, like all things. So here we have a specific sort of a possible implementation of this COUNTIF. We're now again using templates, and we've changed to using class instead of type to specify our type for our input iterator, and we have another one which is some unary predicate. So unary is one argument, gets boolean valued. So this is a function that returns a boolean and only takes a segment. And COUNTIF is to return some integer t, and it's going to take a iterator to the beginning and the end of a particular, and we're going to just go for loop through that, incrementing that iterator until equals last. And if our function acts on the referenced iterator first, we're going to incorporate an answer, and we'll return that answer as the count, as the result of our count. Okay. I think you would need to, this would need to be a genuine iterator. So you'd have to, I think our example here, we're using, so we've got something like vector, standard vector, which has data. So, but you could take something that has a sensible, I think you need something with that sensibly looked. It can't just be, so it's just going to. Don't think you need to inherit from some abstract iterator, no. So just before we gave a specific possible implementation, but you also have implementations provided to you by this. So we have a number of example algorithms that may be useful in the example later. So we have for each applying a function to each element in the range, quite a pattern that comes across commonly. We've discussed COUNTIF, find and findIF, return an iterator of the first element matching or just a match, copy a range if the predicate is true. So if the dependency the function which is deciding if it's correct, true. Transform is quite interesting. Apply a function to an input of elements, storing in the result in a destination. You can overload this to have work on two inputs at once. The swap, so two values, just basically swap two values. This is used wisely. You may wish to provide a way to make your types swappable. So there's more sort elements in ascending order using the greater than operator, some binary predicate provided, and you can provide a lower bound and an upper bound. So it's given a sorted range. Okay, there's a long list of these in CPP-Ref which you can look through and use, but here's a handful that are quite common patterns that you might come across. In the case for each, we need to apply some function to list. But why this isn't that hard to implement yourselves. Why would you use this sort of inbuilt functionality? It's clear what you're trying to do. The information is provided. You read some information about what your intent is with your, this section of code. Using iterators in this way allows you to avoid off by one errors or statements. This works well with other range-based algorithms. It's quite concise if your operation is already defined in a function. But often a range-based for loop is better, but this is quite reusable. Transform can be very powerful. Take a simple case where you take a single range, apply the function to each element, stores a result in an output. Here you're providing the input iterator. So that's data begin at the bottom. Data.end is stored on the last element. And then you can also provide you don't have to provide it as a separate output iterator, but you don't see at the end location. It assumes that what you're providing is the output. So the sort of equivalent of a map function from more programming or map reduce, you can provide the input and the output. So in that case, there's also another sort unary predicate functions which you can apply to that are provided in order to certain operations. That's what I want to say there. Okay, what's the motivation? Is the implementations have been tested by your compiler. You may have done specific optimizations that you won't probably don't want enough. They provide a simplified sort of, you're communicating with someone else who's writing and using this code, or yourself who may have forgotten what you actually intended and was something more complex. So at the bottom is an example of two implementations of the same effect, but using this sort of a order C++ style for loop, and using one of these, and this is giving us iterator of images, and I want to output some iterator that contains all my cat pictures to hold. What you're doing here is you're applying sort of back inserter, which is a particular output. The return from contains a cat, an image, and it's inserting back into the cat pics each time. But the code is much more readable at the bottom. It's very clearly states your intent to the reader what you're trying to do here, whereas the piece of code will take a minute to really understand what's happening and going on. Okay. Now, these algorithms allow you to iterate through and apply type operations to a given container, but you may also want to customize those operations yourself. So algorithms need functions. So you need to decide to sort of provide some function-like object as an argument. You define an argument to the algorithm in order to use them. If you declare one-off functions for one of these, it's kind of, if you're moving this away to some header file or some other location, it moves the co-locality of the use of a one-time use function away from where it's actually being used to do its work. Therefore, you make it harder to read the code quickly. What's even worse is that sometimes you have to create some custom function or class each time, opposed to just a function. And this is where this can come in and help. So to kind of illustrate that issue, if we take the transform here at the bottom, and what we want to do is square the value divided by the rate of transform. So there's a standard vector of x that's passed into this function by reference, so that whatever effect we have in this case we're not having an effect that will be returned, but it's being passed by constant reference. There's no copy being made, but we're not going to edit the values of x, and a float c is passed in. This transform algorithm takes the end pointer of the vector container x and returns the answer into a new vector of float s, and we pass the beginning pointer of that, the iter of that in, and then we apply and add constants onto each element of this to be written answer. Now the issue here is that because transform will only take a function that has a load operator with a single argument, because that's what it's expecting. We can't pass in a constant in and give it two values, two variables into the function. Okay. Should the last argument in transform be the function struct, not the vector? It is this line. Sorry, this. Yes, there should be an f here. There should be square and add const f, not add constant. That's the name of this function itself. Okay. Yes, good spot. This should match this. It should match instead of this. But okay. The point of this is, in order to get the effect that you want, is you want to pass x and c into this transform algorithm, provide a new structure that takes has a constructor that takes a single argument c and stores that as a piece of state, which then can be used by the operator overload that transform calls when it's run in order to give the correct return. And that's because now you've had to define a whole new structure for a one-off usage. You might keep everything together, not have this held in a separate file, and keep the code in one location. So lambdas can help you with this. So a lambda function, aka a closure, does not have a name like functions you are more used to. You can define one inside a function body. You bind them to a variable. You can pass them to other functions. They can capture local variables either by value or reference, or you can do things like capture everything in the local scope. Try to avoid this by default because you need to make sure you don't capture things. They have some unique unknown type, and you may have to auto or pass them straight into the argument because they don't have some you specify when you're calling them, passing them around. So the variable which you assign them to doesn't have a specific unknown type. Okay. Here is the same example now implemented with a lambda. So here we have the same function with the same inputs of a constant reference to a vector floats x and some float c. This function is going to also generate the same floats for the answer and resize it appropriately to the same size as x. But now we define our lambda function in the next line, which is auto equals square bracket c. This is the capture. This takes the value of c and makes a piece of state available to the function body that's inside the curly braces. We have a comment list like we'd be used to. This is what's double z taking in. The function body is going to take a line and it returns z squared plus c, as you would write in the function. There's nothing special you have to do in here. Okay. Now, when we come to call transform, we provide a set of iterators as we did before, but now we're just passing func. And because func is a lambda which takes a single argument, transform is going to call that on each member of x and put the output in answer. This is now much less code that's had to be written. It keeps the location of the operation with where it's called, as this piece of this function isn't reused anywhere else, duplicating code, but you are able to capture state in a much way than you were in the previous method of implementing. And you can make this even worse because do you even need to actually function called func to capture the lambda in a variable. You don't know. You can just pass this straight into the transform. Okay, so we kind of discussed this, but I'm going to go over it again just to make it really clear. So why do you use the lambda as opposed to just using a normal? You use cases where you're going to. So the example here is really around code locality and reducing, keeping things when you want to read the code. It's obvious to whoever's using it to try and find where that particular function has a definition and bring it all together. That helps the user. It allows you to capture and hold this state in an easy way. There are some other sort of, if you've got calls to with sort of variable and constant arguments, it's quite nice to be able to call the same function multiple times in a particular scope and call a lambda opposed to passing everything in a variable times. This can offer some quite nice functionality. But the example here is around code locality, really, and using these out as a way of using these out in a nice way. So just to reiterate, the anatomy of a lambda captures, which is between the square brackets. You just pass in the values, sort of variables from the local scope. This syntax is a lambda expression. You pass in an argument. You have an arguments list to normally define a function. Curly braces give you your function body. This is the normal way you'd write a function body. There's nothing sort of special happening here. From C++11 onwards, you have a syntax where you can specify the return type of this function body with this right-hand side return type definition. Okay. You can capture values by copy and by reference. You either just put in the local variable as with its name or with an ampersand by reference capture. So it just creates a function with the a function object with a type and the single operator load with the name or whatever variable you associate this with. Okay, so as it doesn't have a name, itself does not have a name associated with a variable, it cannot take resolution. Okay, so quick quiz. What does this do? If anyone wants to have any guesses in the chat. Nobody wants to hazard a guess. Yeah, this does. So your local scope, this is to be a lambda with no captures, with no arguments, with an empty function body that is instantly called, so it doesn't. Okay. So to discuss some more of the uses of these we've been looking at, we can have standard template algorithms or similar in passing code in freely. So here's an example of sort. We can also do more complex things, especially if they should be constant. So, so the sort here, let's just go through this in detail. We've got 0 captures molecule A, molecule B, and comparing, we're returning. So these are particle constants, and we're going to affect them with a comparison between the charges of the two molecules and returning whether one is greater than the other is true or false. It's just a Boolean value. That's kind of similar to the transform we've already discussed. We can also use for things like, but we want to say get random numbers of some size, which we pass in as a reference in the capture. And we know arguments explicitly, and we say the return type of this is going to be a standard vector of float. We then, in the function body, have a standard vector of floats as being the answer, and we set the size through the capture, and then we, for every element, we range-based. We then will get random number on the element and return that, and then this is called instantly. So this does not. This gives you exactly what you want, which is a constant set of a constant vector random number. Now can't be you call it instantaneously, and this isn't going to be affected or edited. So these numbers that can't be changed now, and that's set for your calculation. That's one example that's quite useful. Okay. So rules of thumb around being careful with your sort of captures. If your lambda reduces locally, including pass to an algorithm, to pass the algorithms, capture by reference. This ensures that any changes need to propagate. You could pass things into the capture section by reference. You do a load of effects, and that doesn't have any update in the local scope. If you use the lambda elsewhere, especially if you return it, capture by value, recall references to locals are invalid. The function returns. References to other objects may still be valid, but are hard to capture. So if you're going to copy this and pass this around, you can take copies of all the information with the lambda itself. Also, keep lambdas relatively short. More than 10 lines, you should be thinking about moving into a full function instead of a function. The point of these are meant to be short pieces of code. They're not meant to replace the functionality provided by functions. Okay, so we've discussed a lot of iterators. Let's talk a little bit about performance. We started this particular by looking at many ways to iterate through an vector. So we've now added an additional case now where we use the algorithm to just double in place some values. So compare this, these four examples. So the C style, standard vector iterator, the range-based for loop, and now the reach. By using this for some vector of some size, flip the this. And what we see from this is that the C style in the orange yellow color does seem to be slightly quilt using any compiler optimization. So when you come to compile setting -0, there is an advantage of doing this explicitly from this older C style. But if you implement some compiler-based optimization, then everything sort of sits to each other, broadly speaking. Range-based is automatically above. It's not clear that I think, so I look at the notes of this course, it's not clear that there was a good reason why that that, and it could be compiler or test specific, but if you're optimizing this away, the compiler does a very good job. There's really a huge difference between these. So you're not really hurting yourself by potentially making the code really easy to interpret and explicitly writing out yourselves if the optimize your particular implementation anyway. Okay, that brings us back to the traits section. So I'm just going to stop sharing for a second and bring up the practical exercise for this section. So using algorithms. Okay. If you download the, just get back to this. Excuse me, I work in Darwin here most of the time. If you go to this location and download, or have downloaded the repository, there's an example to do. And what this wants you to do is it gives you a number of pieces of broken code in order to implement a set of the algorithms we've just discussed and some lambda functions in order to manipulate a set of random integers and test out your ability to use the set of standard algorithms and the functions themselves. So what I suggest is sort of 20 past 3. If we come back at sort of 10 to 4, and give people half an hour to look at that, I'll be here in the chat available to help anyone has any questions. And then at sort of 10 to 4-ish, depending on how people are doing, I will then go through sort of the example itself, the solutions. Yeah, so we'll get again at 10 to 4. Just before I do the example itself. There are sections where it says where to put code, and it gives you a number of printouts to show that you're doing the correct thing. The exercise is embedded inside the file itself, and there's a make file to go along with it. It's easy to build. So have a play with that and see where you get, and let me know if you have any problems. Okay. Can people hear me again? I assume so. If everyone's had enough time to go through that example, I will work through the solutions or solution to this, and if there's any, there's a couple of issues people are seeing, but we will discuss them as we go. Okay. Fantastic. So Collaborate now won't let me share individual screens, which is really helpful. Oh, will do as long as they're maximized. How odd. Okay. Okay, can people see? I think you should be able to see my okay. So yeah. Okay, Stephen. Sorry, Stefan. We'll have a look at that in a sorry about that. Right. So the example here. Effectively, what we demonstrate is the use of these algorithms. I think I see during the first one, I should make explicit there are two libraries which contain algorithms. One's called algorithm, the other's called numeric algorithms. So there's some bits that are stored in two places. They're included by default to this particular file, but if you suddenly realize you can't get a particular piece of functionality later to use, why? Okay, so this is split into two. Initially, we're just looking at taking some random numbers and sorting them, and then later we're going to look at the Fibonacci sequence and sorting a generated sequence of Fibonacci numbers in various positions. So to start with, we need to we've got a for loop which initializes the vector of some numbers. Instead, can we generate this using a lambda? So to do that, we can use generate part at the beginning of the vector, and then part of this lambda function generate again. And if we, I'm just trying to get this going before that. Just slightly so we see the output. So we're going to do effectively on generation. The second version of generation is different. So we can use this function with the bump, which is print back, and we're going to pass it in nums, and with if we just have so I have generate one is given the outcome just the for loop in this the other sort of world, the C star. And sorted numbers is not actually sorting yet, but it's the first call print, which happens after we generate using this standard generate algorithm and our gen line function. Okay. So we can see different numbers each time. So that's kind of the first thing to look at. So this is quite simple. We're going to iterate through this, and we're going to act. We're going to do a function call and return a value that's going to be missed. Okay. Second thing we want to do is to sort these. from the list of the items we discussed at the beginning of the lecture. Do this step by step because I think it makes it kind of easier to see. So now we have a sorted list from the output generator. Okay. Thing because we're not print statements beforehand, but you can see that the outputs are going to change line by on each section. So at the moment, everything is printed as sorted because we've done no more operations to the nums before the next print. Okay. So that's the sorting done. Next, we can look at reverse sorting in two ways. So first, we can use standard sort again and apply predicate to it, which is provided by the standard, which is greater. That's right. Okay. And second way is to instead use. So I'm just going to undo just sorted, if that makes sense. So we've taken some generated numbers. This item doesn't work very well at the top. We've got standard generate. We've sorted them. I'm going to sort them now with greater than, and I'm going to show. Now I've sorted them. You see, we now go in the opposite order of the previous one by using the same algorithm, but using a different function. There's a way to do this. So I'm going to do that in reverse sorted nums B. But before I do that, I need to first sort the numbers, get into the correct order, else the reverse won't do anything. What's the question here? Okay, just that issue in a moment. So instead of using different ways, we can use reverse. Okay. 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 So it may not look like anything there because we've got no additional printout, but you effectively use different ways to sort and in a reverse order the same set of numbers, and they're producing the same output. Okay. So that's sort of the initial side. Next, we have the Fibonacci sequence. So this is a little bit more complicated. So what we want to do is generate the Fibonacci, the first 47 Fibonacci numbers using standard transform. So to start this, we need to we've got a standard vector of integers called fibs. This is, so we need to set some initial conditions for this. This is where In chat, someone had thought they were getting, well, they were getting an overflow, but that's because they set the initial conditions for to 1, the first two 1 and 1, not 0 and 1. And we're just going, the Fibonacci sequence is going to iterate through and add the previous two elements together to make the next element. The standard transform for this, we use a slightly more complicated version of it than we've discussed so far. Okay. So our vector fit is going to iterate through, starting at begin, but finishing at fibs dot at end -2. I'll explain this in a second. Take the version which has two, which takes another input argument. In total, it takes 2 input arguments, but we provide the beginning point for the second argument. This is begin +1. So effectively, you're starting with the first element of the addition you're going to do to be the current element of the location, and then begin +1, and then we need to provide an output location, which is going to be +2. Hence why we can't go to the end of the sequence, because otherwise we'd overflow the end of the vector. If we had fibs, the end limit would be fibs end opposed to fibs n -2. And that will fill this vector with the correct elements. We now need to provide an operation we're going to use, which is standard plus. Okay. Now that setting up should give the first 47 Fibonacci sequence numbers. So that's this text now. I'm just highlighting here. Okay. So that's the initial generation, and that's where people were sometimes seeing overflows, which was just initial conditions. Okay, so the next we want to have a less than 4 billion, and we want to store them in a new vector. So to do that, we've got a fibs less of a, which is a standard vector of int size. So in order to, because we don't know the number of elements which are billion before doing the calculation, we're going to use a back inserter to sort of like push back onto the end of the vector the values that pass the copy if. So given in the hint copy if, and we're going to use fibs begin, fibs dot end, and then we need our back insert. And take fibs s. Then we need a function which is going to determine our elements that are less than 4 million. So for that, we're going to use a lambda. And it's going to be some int x. We don't have any captures in this case, but we do have some Boolean output, which is going to check something. 4 million in the final row. And then we only want the evens. So we're going to do something again very similar. And now we're operating on the result of the previous, which is fibs less, not fibs. So I'm going to iterate through whatever the length of this vector is. I don't need to know what that length is a priori. Iterate. And again, we want to do it on the back inserter. New vector evens. We have some lambda. We're going to pass this to calculate the evens. I'm just going to read the files. Based on so whether it's even. Okay, run that. So now only even values from the previous list, which remembers the Fibonacci sequence. So we're almost done. Final thing to do is we want sum of this. This is then calculated with accumulate. I want to actually even still begin. And okay. Oh, I missed. Oh, of course I have. I just think that get people to just make set namespace using namespace std. Try to avoid that. Everything like that drive you mad. Okay. And we finally have our final result, which is this sum as we expected. And that all using the algorithms opposed to writing specific for loops. So I find that's quite a nice example of going through how to use these algorithms. In a specific example, there's many applications where you could use this technique in your own codes. Various containers, they don't just have to be vectors of kind of standard types. You can think of many uses for a system. Okay, I'll stop sharing. That is all the content I have planned for today. There's one more day of this course tomorrow, which is going to focus on eigen and a bit on threading, which will happen tomorrow. I will probably turn up at the beginning because anyone has any lingering questions about the content discussed today, but I'm happy to take any questions now people have. If not, we'll take this to an end. Okay, I don't see any questions. So thank you very much for joining us today, and I found this very useful. By all means, send us any additional questions you have. If you think of anything tonight, the rest of this afternoon, and I will be around tomorrow to ask anything else. Have a lovely evening. It's evening where you are. Otherwise, have a great rest of your day. Thanks all. Goodbye.